The third and final coordinate system deals with the cylindrical components r and theta. Now, when do I actually need such a coordinate system? Well, one can use the cylindrical components when the path is known and the acceleration is not particular. So in the exact same conditions as the normal and tangential components. Now, one particular scenario in which the cylindrical components are really useful is when we have motion, which is a combination of a translation and a rotation. And when this combination is nicely set, one can make use of this coordinate system. And you'll see in the problems later on how it's actually very trivial to know whether one should use the first coordinate system or the other. So in this case, the axis is centered at the particle as well, and so we do have a moving reference. But a fixed origin O allows one to describe the position of the object accurately. So here we can describe the position accurately. The r-axis extends radially from the center O to the particle, so that's how we can draw the r-axis, while the theta axis, which is known as the transverse axis, is perpendicular to the r-axis, following the right-hand rule. So how can you draw the r-theta axis? First, you start by drawing the r-axis by connecting the center O to the particle's position, and then by applying the right-hand rule, one can find the theta axis, which is always perpendicular to the r-axis. Now let us talk about the position, velocity, and acceleration. Again, the position needs to be described in terms of the unit vectors, ur and u theta. But again, noting that the position of the particle is always along the radial axis, so it only makes sense to set u theta equals to 0 in that case, and so r as a vector is equal to r times ur as a vector. So r is only defined in terms of the radial component and not the transverse component. Now concerning the velocity is equal to Vr ur plus V theta u theta, where Vr is equal to r dot, which is dr over dt, while V theta is equal to r theta dot equals to r d theta over dt. Now note that the theta dot value is actually the angular velocity, while the theta double dot represents the angular acceleration. So in order to better understand the difference between these two components, Vr and V theta, one should keep in mind that Vr deals with the change in length of the vector r. So let's say that a particle is moving away from the center O, then Vr would be increasing. While V theta is actually describes the rate of motion along the circumference of an imaginary circle of radius r. So this means that if you take the particle, which is at a distance r from the center O, and it's moving with a certain velocity, the V theta component would actually be tangent to an imaginary circle of radius r. So if you draw the circle of radius r in the image on the right, you'll notice that V theta is always tangent to that circle, so it can represent the rate of motion along that circle itself. Now finally, if we want to get the V value in magnitude, so the speed per se, it would be the square root of Vr squared plus V theta squared. Finally, concerning the acceleration for that coordinate system, we have A is equal to dV over dt, which is equal to AR ur plus A theta u theta, where AR is equal to r double dot minus r theta dot squared, and A theta is equal to r double dot plus 2r dot times theta dot. The magnitude is also defined as the square root of the two different components. Now I know this might be confusing. I've just shown you multiple expressions and multiple variables that need to be calculated, but you'll better understand what I'm talking about in the next slide. So you noticed here that we had complicated equations with multiple unknowns, and now we actually want to know how to make use of these equations of motion to solve a problem. So from the previous slide, we know that the unknowns are r dot r double dot, theta dot, and theta double dot. So how do I actually compute these values so we can replace them and get the different components for the velocity and the acceleration? There are basically two different methods one can make use of, and which method to use depends basically on the given of the problem. So if you are given r, the position as a function of time, and theta as a function of time, then you can simply take the derivatives of the two expressions to find r dot, which is dr over dt, r double dot, which is d2r over dt2, theta dot, and theta double dot. So let us look at an example. Let us assume that you were given an expression for r, which is equal to 3t cubed plus 2t, and an expression for theta, which is 5t. Then we need to find the different unknowns. R dot is the derivative of r. So taking the derivative, one has that r dot is equal to 90 squared plus 2, while r double dot, by taking the second derivative, is equal to 18t. Similarly for theta, taking theta dot equals to d theta over dt, we have theta dot equals to 5. Then theta double dot, since theta dot is a constant, would simply be equal to 0. So you can see once you're given an expression of r and theta as a function of time, deriving the different unknowns is very systematic. You just have to take the derivatives twice. Now the second case is assuming we are not given rt and theta t, then we need to derive an expression of r as a function of theta. Then one can apply the chain rule to get r dot and r double dot, then theta dot and theta double dot. So in conclusion, when dealing with a cylindrical coordinate system, one has two methods. You are either given the expression of r and theta as a function of time, or you actually have to derive an expression yourself of r as a function of theta here and not time. Then you apply the chain rule to get the different variables.